All right, let's dive into the periodic table and get to know one of its most, well, let's call them a dramatic family. They're a really tight-knit group, they follow some super predictable rules, but then there's the one member who just loves to break them.
But hang on, what do we even mean when we call a group of elements a family? You know, it's kind of like our own families. It's all about those shared traits, the things you can pretty much count on. And in chemistry, those family traits, they all come from one deep, shared secret.
So, let's get properly introduced to the family of the hour, the halogens.
Here they are, the resonance of group 17 on the periodic table. We've got fluorine, chlorine, bromine, iodine, and the super rare, kind of mysterious astatine. They might all look a little different, but trust me, they are all connected by one single powerful secret. Even their family name, halogen, gives us a huge clue. It literally means salt-producing, and that is their favorite thing to do. I mean, just think of regular old table salt, sodium chloride. Yep, that's a classic halogen move right there.
Okay, it's time. Let's pull back the curtain and look at the one secret that defines this entire family, the thing that explains pretty much everything they do.
And this is it. This little bit of code right here. It's their shared valence electron configuration. Now, what that really means is simple. Every single one of the halogens has exactly 7 electrons in its outermost shell. Not 6, not 8, just 7. Having 7 electrons puts them on this constant, absolutely relentless quest. See, they are so close, just one single electron away from having a full, stable shell, just like the super chill noble gases. And this desperate need for one more electron is what makes them so incredibly reactive. And since they all share this exact same motivation, they tend to follow some very predictable patterns. You could call them the family rules. And you can see these beautiful logical patterns right here. As you go down the family, from fluorine at the top to iodine at the bottom, the atoms just get bigger. And because they're bigger, their pull on other electrons, what we call electronegativity, gets weaker. At the same time, it gets easier to snatch one of their own electrons away. Makes sense, right? But at the top of the family, oh boy, we have the undisputed champion, fluorine. It has the strongest pull on electrons of any element in the entire universe, period. It is the ultimate electron thief. Now, what's really cool is this isn't just about numbers on a chart. You can actually see these trends. Up at the top of the family, fluorine exists as this pale yellow gas. Then you take one step down to chlorine, and the color gets a little deeper, more of a greenish yellow gas. Go down one more to bromine, and boom, we get a change of state. It's now this intense reddish liquid. And finally, we get to iodine, which completes this perfect progression as a beautiful violet-colored solid, from gas to liquid to solid. See? So far, everything is perfectly behaved, perfectly predictable. But this is where our story takes a sharp turn. Because the head of the family, the one that's supposed to set the standard, fluorine, well, it's also the family rebel. It doesn't always play by the rules. So what is it about fluorine? What makes it such a rebel? It's basically a perfect storm of unique properties. It is incredibly, incredibly tiny. It has that off-the-charts electronegativity, and it doesn't have these extra d orbitals that its bigger siblings do. All of this comes together to make it behave, well, anomalously. So here's rule number 1 that it breaks. You would expect fluorine, being the most electronegative, to be the most excited about gaining that one last electron, right? But it's actually less excited than chlorine. And why is that? It's because the fluorine atom is so tiny and its existing electrons are packed in so tightly, they create a lot of repulsion. It's like trying to squeeze one more person into a very, very crowded car. And anomaly number 2 is the bond it forms with itself. The bond between 2 fluorine atoms is surprisingly weak. I mean, look at this. It's weaker than both chlorine's bond and bromine's bond with themselves. Again, it's because those atoms are so small that the electron pairs on each one get too close for comfort, and they start to repel each other, which weakens the bond holding them together. Now, this rebellious streak isn't just academic. It has some really obvious consequences. Just look at what happens when it bonds with hydrogen. Fluorine's insane electronegativity lets it form these super powerful connections with its neighbors, something we call hydrogen bonds. And that is why hydrogen fluoride is a liquid at room temperature, while all the other hydrogen halides, like HCl, are just gases.
So after all this, why are we focusing so much on this one family? I mean, what's the big picture here? What's the takeaway?
It's because the halogens are, well, a perfect case study. They give us this beautiful, clear example of how one simple underlying idea, that electron configuration, can create these predictable, elegant trends. But they also show us that sometimes it's the exceptions to the rules, like our little rebel fluorine, that actually reveal the deepest and most interesting truths in chemistry.
And that kind of leaves us with a final thought, doesn't it? We build all these frameworks and rules to try and make sense of the world, but so often the most powerful insights come from studying the things that just don't quite fit. The anomalies, the rebels. So where else do you see that playing out? It's something to think about.